Good morning, everybody. It is a pleasure to welcome everyone to this colloquium series under our Center for Mathematics and Artificial Intelligence at George Mason University. Some of you are joining us over the summer, and it was a lot of fun, and we hope this fun will continue during the fall semester as well. Before I introduce today's speaker, just a couple of logistic things. Since we have a large number of participants, what we will do is once the talk starts, I will mute everyone and we'll keep it that way throughout the talk. Please make sure that your video is turned off as well so that we can protect some bandwidth. If you have any questions during the talk, then please put them in the chat box and I will ask based on the urgency. After the talk, everyone will have an opportunity to ask questions either via chat or over voice. So that was the logistic part, and it's a great pleasure to welcome Professor Enrique Zuazua as our speaker today. I'll just say a few words about Professor Zuazua, otherwise it will take me an hour if I get into too many details. So Professor Zuazua is currently a chair professor at FAU Erlangen-Nürnberg, and he's also a distinguished professor and director of chair in computational math at University of Desoto in Bilbao, Spain. He's also the professor of applied math at University of Autonoma in Madrid. He's an expert in PDEs, control theory, and numerical analysis, and he's produced many good students. I checked last night on Wikipedia, I think 24, and many of them occupy excellent positions all over the world. I mean, he's on the editorial board of many journals, his advisory board of many institutions, and he's been a strong mentor and a supporter of our group over the last several years. And if I remember correctly, I think I met you, Enrique, first time at TU Munich like 5 years ago or something. So welcome, and we're really looking forward to your talk. So please go ahead whenever you're ready.
Yeah, thank you, Harbir. Yeah, I mean, it's for me, it's a great pleasure to be here with you, and yeah, I feel very much like at home with this audience, and in particular in the frame of this colloquium of this center that George Mason is launching. And well, this is a difficult time, but certainly this is a very timely initiative, and I'm sure this will be very successful, knowing your previous background of say broad scientific interest and your own, say, motivation for multidisciplinary research and your capacity of mentoring and attracting young minds. So let me get to the topic. So Tarpike control and deep learning. Actually, let me tell you how we got to this. It was long ago. It was maybe like 15 years back or so when I was in Madrid. I had the honor of being the PhD advisor of Francisco Palacios. Francisco now is working in Boeing in Long Beach, California. After the PhD with us, he was a few years in Stanford as a postdoc in the team of Anthony Jameson and Juanjo Alonso. And well, the topic at that time, we were collaborating with the Spanish branch of Airbus and also the Spanish INTA, the National Laboratory for Aeronautical Engineering, well, in Spanish, Instituto Nacional de Técnicas Aeronáuticas. And at the time, I mean, the PhD thesis of Francisco Palacios was optimal shape design in fluid mechanics with applications in aeronautics. And for me, you know, as a PD person, well, of course, we all know Navier-Stokes, the Millennium Problem, but I mean, even before that, right? So PDEs in principle are, say, objects that evolve in time. They are dynamical systems. And yes, indeed, you can also consider the steady states. And in particular, in principle, very often, you know, or in the best cases, at least when time goes to infinity, the solutions develop some steady state behavior, right? But for us, PDEs are dynamical systems. And we observed that most of the literature on aeronautic optimal shape design was written in the steady state context, right? And then I was always, you know, talking with Francisco about this. So why is that? How is this justified? Then, of course, you will meet people that are more, say, applied oriented, and they will tell you, yes, but of course, if a dynamical system has the tendency to go towards equilibrium, it is very natural that the optimal shape design or the controls you implement, right, even if they depend on time, eventually when time is large, you know, they get to also close to a steady state, and therefore it's very natural and very useful, of course, and you know, you reduce significantly the computing time to do the computation of the controls or the approximation, the analysis of the controls in the steady state context, okay? And then here I bring you just an example of this. There is a very nice paper by Juanjo Alonso and Michel Colono. It's kind of a dissemination article, survey article back in 2012, where they talk of, you know, the challenges of the new generation of supersonic aircrafts. And of course, one of the main challenges is to guarantee a shape design so that the sonic boom, you know, that, you know, the supersonic aircraft produces is below the thresholds that present very tight, say, regulations impose, right? This is a control problem where the control is actually the initial datum. There is a model for the propagation of the sonic boom. I think is due to Witham or one of these classicals in fluid mechanics, which is kind of a non-local version of the one-dimensional Barger's equation. Then there is a map, an F function. I think they call it the F function, which mimics in a one-dimensional reduced version the shape of the aircraft, right? And then the game to play is how do you shape the airplane, or in the other words, how do you regulate the initial datum, this F function, so that when time, you know, when the wave gets down to Earth, the final datum, the final state you achieve is below this given threshold, right? So, and the time horizon is long. The time horizon is long. Why? Because, well, you know, it takes, you know, this airplane is above 10,000, say, meters high, right? There are many problems of very high, say, societal relevance that, you know, they lead to control problems in long time. So sustainable growth, right? Chronic diseases, climate change. There are many other examples. Okay. So then when you look to the literature on, say, the mathematical literature on controlling or, say, shaping dynamical systems, of course, everyone understands that there is the steady state, there is finite time, and there is infinite time, right? But oftentimes, no attention is paid to how things depend on the length of the time interval, right? And then this lecture is about this. So in some sense, in many practical applications, you are dealing with dynamical systems that you have to tune, to regulate, to control, to design, right? In a long time interval, and I underline the word long because the length will indeed matter, okay? How is it related to, say, to machine learning, neural networks, in particular, residual neural networks that are those that are, say, more easily written in analogy with ordinary differential equations? Well, the argument is very much the same, right? So these are time discrete dynamical systems, and oftentimes, you know, the performance of these neural networks is improved when there are many, say, iterations of this, say, nonlinear map or many layers in your neural network, right? So then the question arises also naturally. So can we, with the same ideas we developed in order to understand dynamical systems, right? In particular in mechanics, as it was our original, say, goal, right? Aeronautics, structures, etc. Can we use these ideas in the context of machine learning? And the answer, of course, is yes, although there is, of course, plenty to be done, right? Now, we wrote the first paper on this in 2013 with Alessio Porretta. This was published in the Siam Journal of Control. And when we did it, we didn't know that the Tarpike theory existed. It was actually one of the kind referees who said, well, maybe you should look at, you know, the Tarpike theory. I never heard that word before. And then I went to Google, and then I found that in America, Tarpike means something like a highway or so. And then, you know, Porretta and I was a bit shocked. I mean, what is the connection? And then we look a bit further, and indeed, you know, John von Neumann back in 45, in the context of game theory, and later Samuelson in 58, he later got the Nobel Prize in economics, they already observed that there is a phenomena which is kind of universal, that actually we implement in daily life all the time, even without thinking on it. And they coined the term Tarpike for it, right? So this is the drawing, right? You are driving from New York to Los Angeles, and then there is a best path. That's clear, right? There is a highway, is the shortest path. It will take you 41 hours to drive nearly 3,000 miles, okay? There are other paths, it will take you longer, right? You know, maybe they are nicer because you visit the lakes and nature and the canyons and so on, but it will take you longer. There is a path which is optimal, and everyone understands that. But there is something else. When you say what is the best path to go from New York to Los Angeles, you know, people will not ask you, but are you departing from office in New York or from the hotel? Or are you going in Los Angeles to the university, or are you going to a shopping mall? So we know the answer is very robust, right? And there is a huge attractor of initial points and destinations that share the same path. So now two people, different people driving from New York to Los Angeles, right? They will share, you know, like 99.9% of the time the same path, right? The only difference in their trajectory will be that, of course, initially, because they are departing from different locations, they will take a short path different, one and the other, in order to get into the Tarpike. And when they exit, also because they are going to different locations, right? They will also take a final different small arc. Okay, so this has been already ongoing in the context of finite dimensional systems. There is a book by Zaslavsky on this on 2006, works also by Lars Grune, also very much motivated by economic theory and discrete time dynamical systems. And as I said, once you see what Tarpike is, well, you could now, I mean, if you want, you can simply quit the talk. Now you know what it is about. It's simply as simple as the meeting point in the airport. I mean, you are traveling, and so your friends are meeting you, you are meeting your friends in the airport. So the optimal solution is that you decide to meet in the meeting point. So you go to the meeting point and then you wait there until your friends come, right? And this is what is drawn in this trajectory, this simplified trajectory that could draw, you know, could represent either the control or the state, because both, you know, the state of the system, the actual quantity you are interested in, and the control both share this Tarpike property. This is what it says. I mean, there is this flat black zone in which you are in the steady state configuration. The control and the state, you know, they are perfectly fine in this location, which is optimal. And then there is an initial arc and a final arc in which each of, you know, the initial and final configurations you choose, you know, have to adapt in order to get into the steady state and then quit again to reach the final destination. This is the Tarpike. And if you think on it, you will realize that you are doing that all the time, right? Also when you take the elevator, right? So you walk, you rush, if you are on a hurry, you will rush to the elevators, but once you are in the elevator, I mean, you don't need to rush anymore, because it will take you whatever it takes to the elevator from going from floor number 1 to floor number 20, okay? Now, when we decided then to, I mean, I'm telling you the story in a more or less reverse, not really chronological order. I told you the beginning, I told you the end, and now I tell you what I was thinking, right? So then I say, well, if I am aiming to prove some kind of tendency of controls to steady states, why don't we see them? I give you an example, the wave equation. We were used to this, right? You can have a look, for instance, to our science review paper back in 2005, where we do the numerics of waves and explain how, you know, dangerous high frequency wave components can be and so on, right? This is a well-known phenomenon. But of course, whenever you compute controls for waves, they are oscillatory, they are chattering, you know? Or if you like, you can also look at them in the space-time, say, version, And you will see that they are driven by characteristics, but they should, right? Because the solutions of the wave equation are driven by characteristics, or by characteristics, if you like, in multi-D in the context of microlocal analysis. And then the controls, it's natural that they do what the solutions are doing in an anti-manner. So a wave is killed by an anti-wave, right? But waves are oscillatory, right? They travel with finite velocity, the controls will do the same. So you cannot really, you don't see the Tarpike phenomena, right? And I will say, moreover, that you don't even expect it. Okay, so when you show this example to these people that are more intuitive, but not really on the analysis of this, they will tell you, well, yes, Enrique, but you know, this is a perversion because you have taken the most complicated model, the wave equation, everything is oscillatory, there is no dissipation, there is no tendency to stability. Okay, so then I said, let's take the heat equation. And actually, the heat equation, I knew that before. So it was when I was a PhD student, I remember a discussion in Collège de France with Jean-Louis Lyons, when he saw for the first time in his collaboration with Roland Glovansky, this path. This is the control for the heat equation, right? And say, but this is the control of the heat equation on the left, and on the right is just a zoom of the final arc of the control of the heat equation. So they got this simulation and they said, well, that's strange. We are controlling the heat equation. The heat equation is very smooth, right? It's diffusive, it's going down exponentially to zero. And the control, rather than doing the same, it looks like a lazy control that decides to do all the exercise, you know, at the end. So that in the beginning it's smooth, you know, it grows up little by little. And then in the end, most of the energy is, say, expended at the end, where there is a lot of chattering and a kind of, say, Tikhonov, highly oscillatory solution of the heat equation. Why is that? In any case, there is no Tarpike there either, right? And here I have plotted the control of the heat equation in the interval 0, 1. I could do it in 0, 100. You zoom, you will see the same. So the amplitude of the control in the interval 100 will be slower, but you zoom, it will be the same. The same for the wave equation. You can take a longer time interval, but the oscillatory pattern will remain. So why the controls of the heat equation develop this kind of final time singularity and oscillation concentration? Why the Tarpike phenomena doesn't arise? Well, one of the comments I had is, well, maybe von Neumann and Samuelson, they were focused only in the finite dimensional case, and maybe you are dealing with PDEs, maybe you should forget about PDEs and Tarpike. Okay, let me give you the example a bit more precisely. Now, some math. Heat equation control. Take a domain, omega, you control in a subdomain, a small omega in green. You take the linear heat equation, you could also make it nonlinear, but just make it simple, Dirichlet boundary condition, an initial datum, an unapplied force or source of heat, capital F, this is the control. And you say, well, given the time interval, 0 capital T, small or large, we will discuss that later. And I want to drive, the temperature to a given configuration, Y star. This is the temperature you like in your room. We know this can be done, right? There were, papers in the 70s by, Fattorini, Russell, people like Tom Seinman that are, here with us today. They are the pioneers of this in 1D using Fourier series bi-orthogonal. That was a very sophisticated, a great contribution. Later, there were articles using Karleman inequalities. This is well known. But if you are a practitioner, what do? You say, okay, I just minimize this. So I want to bring the solution to the final target Y star. So I penalize the distance between Y. I adopt a least square approach, right? Perspective. So I penalize the distance from the solution in the final time to the target. But because the control, I don't want it to be too large either, I also penalize the control. This is a convex quadratic problem. For a linear PD continuity, you have a strict convexity, there is a unique minimizer, this is the perfect wall, right? And then you can write the optimality system, the Pontryagin maximum principle, in this case, simply writing using the adjoint, the Euler-Lagrange equation for this minimization problem. And then what the theory tells you is the control F will be the solution of, one specific solution phi of the adjoint problem. And the adjoint problem is the adjoint in the sense of distributions, right? So is this heat equation in which the time derivative has been switched to, you know, to have a minus there, right? Of course, this model is here posed in the forward sense of time, but you are lucky also because in the adjoint calculus, the initial time of the original equation becomes now a final time. And then the adjoint equation is well posed in the backward sense of time. Now, if you look to this adjoint heat equation, then you say, well, but then it fits, right? This is exactly what Glovansky and Lyons were seeing in their simulations. Why? Because if you compute the solution of this adjoint heat equation, starting from a final datum at time capital T, which is very complex and very oscillatory, this is the pattern you will see, something large at final time, so that when you go down on time from capital T towards 0, then the amplitude of the solution will be dissipated and will going down, right? With oscillations that will eventually attenuate, because as you know, the Gaussian eventually, you know, mixes everything up, and then eventually the solutions have the tendency to have either a positive or a negative sign depending on who wins, right? Then that fits. So what they were doing numerically is in agreement with the theory, but again, you don't see the Tarpike. So why? Okay, so the conclusion is that, you know, although we expect some kind of asymptotic simplification on the controls, this doesn't seem to be the case for the heat equation and for the wave equation, and I have explained you why. This doesn't occur because for the heat equation, the control is the solution of this adjoint problem, which is, you know, develops this lazy pattern in which most of the oscillations, most of the job is done at the final time. And in the case of the wave equation, simply because the adjoint of the D'Alembert operator is the D'Alembert operator, and then the solutions are oscillatory, as you see in the numerical simulations. Now, what is the remedy? So maybe there is something we forgot. We said, okay, I want to penalize the target in the end because this is what I want. I want temperature at the end to be Y star. I have penalized the control. This is something natural to be done, but I didn't penalize the state. And this is something also I like to do, right? Because, you know, you have to control a system, in particular if you are thinking then maybe moving into the nonlinear context, and you want to control the system not only being, say, conservative in terms of the resources you are burning, but also in terms of not getting too high oscillations that will be then probably an obstruction in practice, because you will go beyond, say, the constraints and thresholds you are given, and in particular they can be very risky in case of nonlinear phenomena. So it will be much more natural also to penalize the state. Again, very simple. Linear, quadratic, convex in a Hilbert space, coercive, everything. So there is a unique minimizer. The minimizer is characterized by the Pontryagin maximum principle, the optimality system. Is the same as before, except for something. You see it here in red. Because of the Y term on the functional, now you have a Y term in the adjoint equation. And because of that, now this optimality system is not as before, it was decoupled. I could first compute phi and then go to Y. And this is how I explain the behavior, the singular behavior of phi. Now, I cannot tell you what phi is if I don't know Y, but I don't know Y because I need phi. So this is a real coupled system, forward, backward, right? There is an initial condition for Y, and there is a terminal condition for phi. And when you compute, right, the spectrum for such systems, what you see is what is plotted here down in this slide, in which part of the spectrum shifts to the to the left of the imaginary axis, and the other one is to the right. Meaning that in this dynamical system, if you think now in the forward sense, as we are used to do in the context of Cauchy problems, there is a projection which is stable going down, and the other projection which is, say, unstable growing exponentially, right? And this is precisely what explains this pattern on, say, the Tarpike, right? There is the first arc is the stable one, then you remain in the steady state, and then the final arc is the unstable one, which corresponds to the spectrum to the right of the imaginary axis. Okay, now assume you want to do numerics. So the first thing you have to do, of course, all these phenomena are seen in long time. As you can imagine, if the, as you can imagine, if the time interval was not long enough, right? Let me see if I can capture my slides again. The name is filled somewhere. no, as George Mason. Seems there is a problem. Can you see my screen?
No, we cannot see your screen.
Something went wrong. Let me open it again. Okay, but I am on Zoom. Let me now try to share again. Okay. Okay, can you see it now?
Perfect.
Okay, let me go then back to the point I were. Okay. So now, all these phenomena, of course, occur in long time, right?
Enrique, maybe make it full screen, please.
Yeah. All these phenomena, you will only be able to see it in long time, right? And this is where I said that many people, after we did this, they realized, oh, actually, you know, we could have seen that before, but we didn't see it because our computations of the control were done on time horizons that were not long enough. Of course, you see this flat lag here in this trajectory that is drawn there. You only see it if the time horizon is long enough. Because otherwise, if you do the control of a dynamical system on a time horizon that is short, simply the initial arc and the final arc superpose, and you see a very oscillatory pattern, but you don't see this flat region, right? This is why in many problems in which the Tarpike phenomena is there, people don't see it simply because the time interval in which they are doing the simulation is not long enough. Now, of course, if you want to do long time simulations, you have to, you know, consider your numerical scheme to be in some sense well balanced or symplectic or geometric. And this is the typical example, you know, like Aurora Marica, former member of our team, did this simulation based on, you know, on the algorithms in this book by Harbir and collaborators on symplectic integration, in which you say, well, I have a nonlinear harmonic oscillator. I know solutions are periodic. This is the red circle. If I do simply naively Euler explicit or Euler implicit, I will not be able to capture the periodicity of the solution. It will either go to infinity or shrink to zero. I need to guarantee that I take a symplectic algorithm in order to make sure that I capture the periodicity, right? The same in the context of hyperbolic conservation laws, where people talk about well-balanced numerical schemes and so on. So this is the first warning. I mean, when you are doing numerics, because we are interested on control problems in a long time interval, I mean, this can be challenging, and in particular, you need to, you know, use numerical algorithms that are well behaved asymptotically. Of course, not only this, in practice, people have developed all kinds of algorithms in order to be able to track, say, and control trajectories in long time intervals as model predictive control, right? What we did in this paper with Alessio Porretta from Rome, Tor Vergata back in 2013, we said, okay, let's try to prove something, right? Actually, we were, I jumped into this with him because I have seen a previous paper he has written with Pierre Lyons and collaborators on mean field games, where they were developing tools that I felt could be of some use in this context, right? So we said, let us consider the simplest A-B problem. So this is the linear dynamical system driven by A, control being given by B. Here is written in finite dimension, but this theory you can adapt it to semi-group context so that you can in particular cover the wave and the heat equation I was discussing before. And now I minimize a functional in which, I mean, this is one of the possible cases where you want to, your trajectory to track a given, say, you know, to be close, to remain close to a given reference point, X star, right? So you want to do that, then you will minimize a functional in which you penalize the control U squared, but also the distance from X to the target X star. Maybe you are not interested on the full target X, but just on some projection. This is why there is the matrix C. You can write down the optimality system, and then you know the control will be given by a solution of the adjoint problem, P, but now when you look to the equations satisfied by X and P down here, you will see that the system is coupled again. One equation forward, the other one backward, right? So what do you need to guarantee that there is Tarpike, that the spectrum splits into the left and the right, as I have shown you before? Well, in order to make it more precise, how does Tarpike theory behave? You say, well, because I don't still understand well the dynamical system, let me first consider the steady state problem. The steady state problem is very simple. You just chop off time. So the dynamical system becomes, now this static problem, AX equal BU, linear algebra, or an elliptic equation, if you wish. You replace the time integral, the cost, by an static cost, right? And then the optimality system is the same, except that there is no time now. And then this gives you an optimal steady state configuration U bar X bar, right? Then you will get the Tarpike, but in order to get the Tarpike, you need a number of, basic conditions to be fulfilled by your dynamical system. The first one is that the original system is controllable, meaning you can drive the system wherever you wish. And the second one, because the problem is all about dealing with the state equation and the adjoint equation all together, you need a similar condition also for the adjoint system. In the context of, say, finite dimensional system, this can be written in terms of linear algebra, right? These are the classical Kalman rank condition. But the message here is, be careful, because even if you were doing just classical optimization by least squares, and you were ignoring more, say, sophisticated dynamical control properties as controllability, right? Which is really whether you can drive a given, say, dynamical system to a final configuration. And this can be quite tricky, geometric, or in the context of PD, quite sophisticated, using microlocal analysis for waves or Karleman inequalities for heat. Even if you were not interested on this, you will have to go through this if you want to understand the Tarpike theory. And then under these conditions, then this is how the Tarpike theory, looks, right? What we are saying is that when the time horizon capital T is getting large enough, the optimal control U superscript capital T and the optimal state X superscript capital T, that in which capital T is just a parameter for the length of the time interval, depending on time, right? They will be close exponentially to the optimal steady control and optimal steady state, respectively. And then on the right-hand side, you have a double exponential. Why? Because you have, two boundary layers, one initially and one in the end, due to the fact that you are dealing with this forward-backward, say, coupled system. This is what the theorem says. And as I said, this is true also for PDs. So in some sense, when we were discussing the wave equation and the heat equation, and we were seeing that they seem not to behave according to Tarpike, the answer is simply they didn't behave that way because simply in the examples I have given you, I was looking to the optimal control and I have forgotten to penalize also the state, right? So the message is when you are dealing with optimal control problems, even if you don't need it, you should penalize the state, because in this way, in particular, you will gain the Tarpike property, something that, of course, is very nice, not only from a dynamical system perspective, but also from a computational perspective, because you begin by solving the static optimal control problem, and this already gives you, the actual solution 90% of the time. In this drawing also, you understand why you need controllability, right? Why? Because, of course, you can always define the static problem and optimize it. But then I'm saying the Tarpike needs to bridge from the initial configuration to the Tarpike. And this is precisely where the controllability occurs, right? Otherwise, if the system is not controllable, there could be an ideal steady state optimal configuration, and you cannot get there because you simply cannot reach in, right? This is like, you get to the airport, you want to meet in the meeting point, but unfortunately there are some works and there is a barrier you cannot cross. So you need controllability to really implement the Tarpike strategy, right? Good. Proofs. If you look to our paper, there are like 3 ideas of proofs. I just give you the idea. The 3 of them are very natural. The first one is dissipativity. Actually, in all this optimality system, in the linear context, when you go to nonlinear, things get much more tricky. Basically, there is a Lyapunov function, which is simply the product of the state and the P. You take the time derivative, you simply play with the algebra, and you will see that the time derivative of this scalar product, in L2 if you are dealing with PDEs, or in the Hilbert space H, or in Rn if you are in finite dimensions, then this is negative. And this is where you see that the fact that B, the controller, and C, the projection you are penalizing, are strong enough is important, because this will give you more and more, say, coercivity of this Lyapunov function. Unfortunately, the proof is, say, more tricky than in the classical Lyapunov theory, because now time is not only going, from 0 to infinity, but as I told you, time is evolving in the forward and in the backward sense. This is why even if you have this, say, dissipativity property, the proof is still tricky to, out of this, prove the exponential convergence result I have told you. The second proof is Riccati. I mean, you say, well, the time horizon is getting large. It's finite, but it's getting larger and larger and larger. So why not considering the infinite time interval? If I consider the infinite time interval, this is the linear quadratic regulator in infinite horizon. And we know by Riccati theory that the solutions decay exponentially, and they are actually given by a feedback, the feedback operator, given by the Riccati solution, right? Okay, so then you have this exponentially decaying arc. Is this the full solution to the finite time problem? No, because in the finite time problem, even if the time horizon is very long, there is a terminal condition at time capital T. So you have to chop off this, say, exponential, which gives you an initial guess, but you have to build an iterative algorithm so to correct this, say, decreasing exponential to match the terminal condition. This is the second proof. And the third proof is in the spirit of singular perturbations. And maybe this is the one that people in PDE will like the most, right? Because you say, well, I have to deal with this, say, control problem in the proof number 3 down there. I have to deal with this problem in a time interval that is getting bigger and bigger and bigger and bigger. But, we don't like to do that. This is like when you are doing shape optimization, you do a change of variable to bring all these moving domains into the reference domain. And this is how you introduce the Hadamard derivative and so on, right? So we don't like moving intervals. We like to have, all the problems, depending on parameters, fine, but all defined in the same reference domain, right? So what we do, right? We shrink the time variable from t into st. So now s is a new pseudo time, right? And then in the new model, what we have is 1 over capital T parameter in red here, which is penalizing the time derivative. But the time is going to infinity. So what is this equation doing? Now this equation is defined for s. It should be s and not t in the time interval 0, 1, right? Now this equation is evolving from being a time-dependent PDE or time-dependent dynamical system into the steady state equation, because you are penalizing the time derivative. And this is another way of explaining why Tarpike occurs, simply because by scaling of time, right, the time dynamics, the time derivative, the sensitivity with respect to time is going down to 0 due to this penalization. Okay, now what about nonlinear? All was linear so far. What about nonlinear? Then we said with Alessio, let's try. Take the cubic heat equation. It could not be simpler. I mean, the cubic heat equation is very dissipative. It's very nice. You can solve it using, the classical energy methods or the ones you like. Right? We know solutions go down to 0. And let's do a simple optimization problem in which now I say, well, it's the same as before, changing a little bit the notation. I want to penalize the control f squared, and I want also the trajectory to be close to, the configuration I like, because I am driving, right? And I want the temperature in the car to be 19. So YD is like 19, okay? So this is the classical tracking term, and the second one is the penalization of the control. Again, this problem is not convex anymore, although the functional looks quadratic, there is a nonlinear dependence of the solution on the control, and this functional is not quadratic, but it doesn't matter. You apply the direct method of the calculus of variation, and you will find a minimizer using the compactness property that you can gain easily by the regularizing effect of the heat equation. There is a global minimizer. You write the optimality conditions, and then you have again a coupled system. Of course, now the state equation remains nonlinear, y cubed, and you see the equation for phi in red. Of course, because the adjoint is the adjoint of the linearized system, the y cubed now becomes 3y squared phi. The equation on phi is linear, but the way y, the state, enters in the equation of phi is still quadratic, because it comes from the derivative of the cubic term, right? So this is a nonlinear system. And this system is tricky. You see, I mean, this is the kind of exercise you could, I mean, if you like to make life difficult to your students, right? You are teaching a course on evolution PDEs, and now I give you this and I tell you, okay, prove that this system has a solution. Well, I mean, you will never get it. I mean, this system that is for one equation is the initial condition is at time t equals 0, for the other one is at time capital T. The system is coupled, one equation is going forward, the other one is going backward. You will never be able to solve it with the ideas of the Cauchy theory. Now, if you know that this is the optimality system for the optimal control problem I written before associated to the semi-linear heat equation, then you will say, well, professor, this problem is trivial. Please give me another one more difficult because the solution of this system exists because there is a global minimizer for this problem. But this explains why understanding how this system forward, backward is hard to deal with, right? So what we did, well, we linearized, right? Where do we linearize? We take, according to the Tarpike theory, we take the corresponding elliptic problem, we minimize for the same price, calculus of variation, compactness, etc. We get the optimal steady state minimizer, or unoptimal, I should say, steady state minimizer. I linearize the system around that steady state, right? And then what you see as equations is that, well, you see the equation Z is the linearization of Y, so it remains the one you expect. If you linearize the cubic equation, then you get, you know, 3 times a potential, which is Y bar squared, Y bar being the optimal steady state. Then the adjoint variable psi in the second line, you see, oh, but now you get an extra term in blue. So why when I do the linearization of the second one, I get an extra term? Well, it's very simple because I have to compute the derivative of 3y squared phi. And when I linearize this equation, I will have to linearize it with respect to y, and I will have to linearize it with respect to phi. I mean, the first term here is 3y bar squared psi is the one I get when I linearize with respect to phi. But then I have also to compute the derivative with respect to y. And this will give me a 2 more, so 6 times y bar, phi bar, right, multiplying by to z, right? Okay, so what is this? This blue term on the right-hand side was not expected, right? It's kind of strange. On the other hand, you revise things, and it's correct. But of course, it's related to the Hessian of the problem you are considering, right? Because the adjoint is already related to the sensitivity, to the first derivative. We are linearizing the adjoint. So we are looking to Hessians of functionals that are not convex, right? Okay. So, but if you write it down that way, as I did it, then you realize that, well, in fact, it doesn't look so bad because it seems that I am dealing with the equation for Z, which is now a linear, nice heat equation with a potential, but the potential is positive, the problem is very well behaved. And the optimality system linearized one I have on the top is just the optimality system for a linear quadratic regulator problem in which I am minimizing a cost functional of the same form as before with F and with Z, but for which now, because of this strange term on the right-hand side, 1 minus 6y bar phi bar, right? Because of that term, there is a multiplier rho, right? Which is that one precisely, which is affecting, you know, the penalty I have on the control. And then you say, well, but this is a very nicely behaved problem under one condition. What is the condition? Is that rho needs to be positive, right? Because otherwise, I don't even know whether this problem is, you know, is convex. I don't know whether there is a minimizer. So I need rho positive to make it nice and coercive. And for making rho nice, how do you guarantee that 1 minus 6 something which is just the product of the state and the adjoint state for which you don't have any information on the sign? How do you guarantee that this is positive? Well, because, you know, you assume that y bar, phi bar are small. And this is why our theory so far on this topic is limited to the case where the target in the nonlinear control problem is small. And there is plenty to be done to understand, you know, more complex problems, right? So this is how the theory was until recently when we got more involved in this, say, neural network business. But what I want you to keep in mind is that, of course, from a mathematical point of view, there are very challenging analytical problems to deal with this in a more sophisticated setting, right, of nonlinear problems with large targets, right? That will take a lot of time before we understand that completely. But there is something you can keep, right? Is that you can also, as you do on your daily life, when you are facing an applied problem in which you have to deal with the control of a dynamical system, you can always apply the Tarpike idea in a, say, quasi-Tarpike manner, which consists on saying, first step, I consider the steady state problem, I compute the steady state control and optimal state, and then I simply build this piecewise linear arc in which initially I control to the steady state, I remain there, and then I quit. And this is precisely when you do, when you take an airplane, you take off, then you stay, you cross the ocean in a more or less steady manner, and then you land again. Okay, this is the Tarpike philosophy that is extremely efficient, reduces computational cost and give you, again, as I said, this does not make sense really when capital T is too short. And this is what is also said in that quote of Samuelson that you can read later from the slides, where they say, of course, the Tarpike makes sense when the origin and destination are far enough, right? Because otherwise, if you have just to cross the street because you live on campus, you will never take the highway, right? You will go straight. And this is the case where the initial and the final arc overlap, and then there is no room, there is no time enough for this steady state to manifest. Okay, the second part, what about deep learning? You can find the first draft of our paper with our team members, Carlos Esteve, Borjan Geshkovski, and Dario Pighin, especially Borjan, who is the one who is writing a PhD, is the one that has more, work more on this. It's very natural to bring these ideas to the context of this deep learning, right? So the simplest example is these classical problems in which you are classifying, you are trying to match, right? Basically, from an analysis perspective, because of this beautiful theorem by Sivenko, right, who says that, well, using neural networks, you can approximate everything. It's like Stone-Weierstrass, who said, well, every function can be approximated by polynomials, right? Yeah. It was Stone-Weierstrass? The density is Stone-Weierstrass, right? Yeah, I think so. Then Sivenko says you can do the same using neural networks according to, you are using the sigmoids. If you then read this original paper by Sivenko, I really recommend you. It's a beautiful analysis paper where you use Han-Banach by duality, and then in the end there is kind of a contradiction argument, but things are trickier than for the classical approximation of the identity using Dirac's, because here you have to deal with hyperplanes, but the last lemma of the paper is to say that any function in Rn that is 0 in every half space has to be 0, and that's the end of the proof, right? Okay, so finally, you can really approximate, right? Make sure that you build a map that is, say, classifying, the different, say, classes of residuals in the corresponding container. I think here there are only 4. I think in Germany there are more containers than 4, so things can get more complicated, but I mean, you can always claim. If someone says there are too many containers, this is too complicated, you can always tell him, okay, so read Sivenko paper, and then you will know whether, this plastic bag goes into yellow or into the other one, okay? So now recently there was a move to say, well, you can increase in dimension as Sivenko did, or you can try to keep the dimension of the Euclidean space in which you are working moderate, because that would make your life easier, and then iterate, so gain many layers, repeat the nonlinear process many, many times so that you can still keep the density, to be true, right? And then you say, well, but then in the end, we are building a discrete time dynamical system, right? So we have the sigmoid sigma, right? Which is kind of this arc, hyperbolic tangent, or this, say, other ReLU, say, piecewise linear truncated, say, absolute value function, right? X plus in the context of PDs, ReLU in the context of, say, machine learning. And then you have weights. And the game, right, is that you have to, in every step of this time discrete, say, iteration, you are allowed to choose the weights WK and BK, in which you are simply with BK, you are translating the data you have, and with WK, well, this is a matrix, so basically you are rotating and you are, you are pushing, you are dilating, like as you do in classical, say, linear elasticity, right? And then you repeat again and again. So what is the link of this with control theory? Well, is that BK and WK can be seen as controls, right? So far, we are in the context of nonlinear, say, discrete time dynamical systems. And then the game to play, again, will be how do I choose the optimal weights, BK, WK, so that when I try to match the initial data XA into their corresponding labels, so in here, try to find the corresponding, recipient for every type of residue, right? Match the X's with the Y's, right? I just penalize the distance. So again, this is an optimal control problem, right? Okay. Now, in the context of residual neural networks, people said, well, you can even make, these sigmoids to operate in a more moderate manner. So let me just apply an increment, right? So I don't apply sigma fully, but I just use sigma to correct my previous guess. So then you see that you get a, say, dynamical system that is behaving more smoothly. And actually, when h goes to 0, you see that you are back to the nonlinear ODE setting. So you see now that when you write the nonlinear NODE model in the middle, you are back to nonlinear ODEs, the controls being WT, multiplying the state, and BT, which are this shift, right? And then you can say, okay, again, I want to control this nonlinear system, so to make sure that in the end, every individual gets to the corresponding final destination. So you see, this is now again a control problem where you have plenty of parameters to be controlled, because if X lives in dimension n, W is a matrix of dimension n, so there are plenty of controls, right? And B is also of dimension n, so for W, you have n squared, and for B, you have n when you are in dimension n, right? But on the other hand, the problem is more demanding as the classical one in control theory, because normally in control theory, you are asking that every initial point goes to the corresponding, you are just dealing with one initial configuration and you compute the control for this specific one. While here, you want the nonlinear, say, control process you build to be, say, capable of classifying, of sending all the initial data into the final targets, the corresponding final targets, simultaneously. So this is like a simultaneous control problem in which you want to build universal controls that are able to handle many, many, many different configurations simultaneously. In any case, you can solve that from the optimal control perspective. And then you can try to answer to the question of what do you gain by adding many layers? So why do you really improve the performance of this classification algorithm, right? When you repeat more and more. In other words, why does it, behave better when you increase time in your control problem? Well, then, this is very much like, if you try to compare with my previous lecture, this will be the case where there is no Tarpike, right? Because when you look to the formula in SL, you see that on the right-hand side, I'm penalizing the controls W and B. For mathematical reasons, I penalize them in H1, so to have compactness, but I am only penalizing the final arrival point. I don't pay attention, I don't track how far the trajectories go. So in this case, I don't expect to have Tarpike. Still, when you increase the time interval, you expect to improve the behavior of the system. And actually, you can see that by the scaling argument I have told you before. And in this theorem, we show that as time goes to infinity, right? If you implement, say, residual neural networks in this manner, right? The classification you get becomes, as time goes to infinity, closer and closer to the optimal steady configuration you can really expect, right? And this is what is shown in the video. I do it first when the time is not too long, not too many layers, then with more layers, and then even with more layers. And you see how you see the picture on the left, the initial points, blue and red, that you wanted to split, you know, put reds to the right, to the left, and blues to the right? In the first video, the time is not too long, so you succeed reasonably well. In the second one, the time is longer and you succeed better. You see a better separation of red to the left and blue to the right. And when you increase even further the time interval or the number of layers, you see that this is much more successful, as shown in the final picture, in which you see almost an optimal separation of reds and blues. But if you observe this video, right, again, you see in here, there is no Tarpike. What I'm telling you, you have to distinguish this with respect to, you know, as I did in my previous lecture. I'm guaranteeing you have a final good, say, separation. You get to the target, but this is not Tarpike. Why is not Tarpike? Because you see that trajectories don't never stop oscillating during the whole time duration. Now, you say, well, maybe this is costing me too much energy. You know, trajectories are oscillating too much. How can I avoid those oscillations? How can I succeed on building residual networks that classify? Yeah, I'm done. Sorry. The last slide. How do I build this residual neural network in a way that I classify well, but on the other hand, I avoid these oscillations? Well, we know the answer from the previous part of the lecture. I want Tarpike, because then I increase the number of layers, but because of the Tarpike property, oscillations will be avoided because the trajectories will remain smoothly on given, say, specific steady configurations. And what do I need for doing this? Well, I need to penalize the tracking term, the state. So if now I build the new residual neural network, penalizing also the time integral, not only the final time, then I have a result of, say, Tarpike type, right? Exponential proximity to the optimal steady configuration. And then when I draw, I see that indeed the behavior of the neural network is much more smooth. And in particular, you know, it behaves according to this, Tarpike principle. So here is the list of collaborators in our group that have been writing different aspects of the theory. Here are the nice pictures. And with this, I would like to thank you for your passions. Also to thank, you know, the institutions that have been collaborating on this, the Friedrich Alexander University in Erlangen, Autónoma in Madrid, and Deusto University in Bilbao. And also, of course, the two main funding agencies that are keeping our, say, team active and alive, the European Research Council in Brussels and the Alexander von Humboldt Foundation in Germany. Thank you for your attention.
Thank you, Enrique, for this very interesting talk. So we have time for questions. So if you have any question, you can either put it in the chat or you can unmute yourself and go ahead and ask.
Yeah, Enrique, I have one. For the semi-linear problem, the Turnpike property, okay, like you explained that well, that to have, you know, in order to solve the problem, you need that the target is small. But intuitively, outside of the math, intuitively is really why the target must be small.
Yeah, I totally agree. And actually, if you do the quasi-Tarpike in here,
yeah,
here you don't need the small, right? And this is why, thank you for your question, Mahamadi, very pertinent. Actually, in this drawing, you see that I have put the blue lines and the red line. Why? Because if you are in a nonlinear problem, there could be several minimizers, right? Local minimizers.
Exactly, yes.
If you are looking for the optimal, say, the global minimizer of the steady state problem, you are unlucky and you get to the local minimizer. Still, you can do something. This will be the red path, right? Then you will say, oh, you know, I remember the talk, you know, on Tarpike. So I will take the ref local minimizer. I will get there, I will stay there, and then I will quit. But then if someone finds a global minimizer of the steady problem, this other person will do better, because going down deeper in the long time duration, you see, this is what explains you that it's very hard to do better than Tarpike. Actually, when you start thinking